Welcome to AI Citizenship for Clinicians. This is our first lecture in Module 1 of the series, titled What is Artificial Intelligence? Our goals for today are twofold. First, we'll introduce some key vocabulary and provide a very high-level orientation to what we mean when we say artificial intelligence, both to refer to a collection of technologies as well as a field of research and study. Second, we'll introduce the basic components of modern AI systems. Taken together, this will set us up with a foundation for future modules, which will delve deeper into how the technology works, as well as its promise and pitfalls within healthcare. In order to understand what we mean when we say artificial intelligence, it is helpful to think first about what we mean by intelligence more generally. Now, this turns out to be very challenging. It's actually been the subject of hundreds of years of debate amongst philosophers and biologists, neuroscientists, other scientists, and as such, there's no official or uncontroversial definition for intelligence. But for our purposes, we can think of intelligence in terms of abilities to do things like reasoning, which is synthesizing information to draw new conclusions, learning, improving on a task given practice and feedback, or generalization, extrapolating information and insight and knowledge from one context and environment into another. And with this in mind as a functional definition of intelligence, we can think of artificial intelligence as a general term for any artificial or non-natural, perhaps human-constructed system that's been designed to exhibit one or more of these traits. Just as we might use the question of what intelligence is as we begin to define what we mean by artificial intelligence as an entity or collection of abilities, it may be somewhat helpful to orient ourselves to the field of artificial intelligence by considering how it relates to other areas of science and engineering. Now, just like with intelligence itself, there's no official or unambiguous definitions here, and I really provide this slide primarily as a reference point given that you're likely to be exposed to these terms in the future. But I will briefly comment that artificial intelligence as a field of research is typically focused on asking the question of how do we construct entities, typically computers, that exhibit traits that we typically ascribe to intelligence. Now, this has a lot of overlap with existing fields such as computer science, which asks the questions of what is it possible for computers to do and with what efficiency. Meanwhile, fields like statistics ask questions such as, given a collection of data, what is it possible to infer or learn from that data and with what reliability? When you combine these insights together, you eventually arrive at the field of machine learning, which asks roughly, how do we program computers such that they can learn from data and experience to improve over time and eventually exhibit behaviors that we traditionally ascribe to intelligence? Computer programming and data science are two other fields you may see referenced a lot. They tend to be more practical, and we include some informal definitions here for your reference. Finally, as we wrap up this first half of the lecture, it's helpful to be able to think about artificial intelligence in terms of the families of methods that researchers use to try to build intelligent systems. These methods are often described using a Venn diagram, as we've done here. In the outermost rung, we have artificial intelligence in general, which represents the use of any method to try to build intelligent abilities into a computer system. This may not involve learning at all. For example, a computer program might be provided with a list of facts about the universe and be designed to apply logical operations over these facts to make deductions and adapt to new circumstances. Machine learning is a specific approach to artificial intelligence, which, as we've described, tries to build computer systems that can improve with experience and exposure to data over time. This typically involves the use of statistical methods, but this could be any type of statistical pattern recognition method. Moving one rung deeper still into this diagram, we have deep learning, a specific family of machine learning methods that use artificial neural networks, an approach loosely inspired by neuroscience. Deep learning is powerful because these models are extremely flexible. With exposure to sufficient data, deep learning models can extract extremely nuanced patterns and learn to perform very complicated tasks, often at the expense of what we call explainability, which is our ability as humans to unpack exactly what the model is learning and how. Finally, we have large language models, which have become extremely popular over the last several years and include models such as ChatGPT. Large language models are a specific type of deep learning model which are trained to operate over text and have been shown to be extremely powerful tools which can be adapted to many downstream tasks. For the remainder of this lecture, we're going to get much more practical and delve into the basic components of modern machine learning systems, an understanding of which is going to provide a key foundation for nearly every subsequent discussion we're going to have in this course. So what does artificial intelligence look like really in practice? The vast majority of AI systems that you interact with over your career will take the form of a computer program or device that accepts some input, processes it using a machine learning model, and generates an output. The input to those AI systems may take any number of forms, including imaging, text, signals like EEG or ECG measurements, or laboratory values. Likewise, the output of an AI system may also take multiple forms. For our purposes, it's most useful to think about the following four. First, an AI system may generate a classification, an output label of the data according to some preset group of categories. Second, an AI system may perform predictions, perhaps the probability of an event taking place in the future. Third, an AI system may be generative, outputting new content, whether that's in the form of text, images, videos, or another format. Finally, AI systems may be configured to be able to perform actions. Now, ultimately, these types of outputs are not necessarily mutually exclusive, particularly with generative AI technology, which may generate text, for example, but that text can be used to generate classifications or to initiate actions. But it's still often helpful in framing artificial intelligence problems to be able to think about these sorts of categories that we outline here. Okay, so we've talked about the inputs and we've talked about the outputs of a modern AI system, but what is actually sitting here in the middle? Again, it can be a wide range of things, but the key concept with machine learning powered AI systems, which is the vast majority of modern AI systems, is that sitting under the hood is a statistical pattern recognition method, which during development can be shown tons and tons of examples of the input data, which can be used to train or tune the parameters of these internal statistical models so that it can be prepared to generate the desired type of outputs. Two examples of analytic methods that may sit at the core of a machine learning model include linear regression and deep learning. Linear regression is sort of the classic method for much of modern statistics, including analyses done just for human use and not involved in a machine learning system at all. Linear regression is comparatively easy to implement and to analyze once it's been implemented. On the other end of the spectrum, deep learning is a much more powerful approach to pattern recognition, which we'll discuss in a bit more depth on the next slide. This may be an intimidating slide for certain members of our audience, and I want to assure you that the technical details here are not going to be essential for any further content in the course. However, given that so much of the incredible progress in artificial intelligence over the past several decades has been powered by deep learning technology, it may be helpful or at least interesting to understand a little bit more of how these work inside. Deep learning technology is powered by what we call artificial neural networks. As you may recall from biology, a key fundamental unit of natural intelligence is the neuron. Neurons receive inputs from multiple external sources, the signals from which are summed up in the cell body, and if a certain threshold is reached, will trigger an action potential which is sent down the axon and exits at these axon terminals, which can in turn be used as inputs to subsequent neurons. In the mid-20th century, researchers developed so-called artificial neurons, which are simply mathematical models designed to mimic the function of real neurons. Namely, they receive a number of inputs, which get summed together in a weighted fashion, the weights of which are learned by the neuron itself, and then transformed into a consensus output. But just like with real neurons, the real magic comes not when you have one artificial neuron, but when you chain them together into a so-called artificial neural network, in which the outputs from one neuron becomes the inputs to the next. As you can see, artificial neural networks are configured in so-called layers of neurons, which each become the input to the next ones. And as you proceed deeper and deeper and deeper into the network, the collective capacity of all of these neurons adds together to become extremely expressive and powerful, both for detecting patterns in data, as well as effectively generating internal decision processes that can be used to generate potentially sophisticated outputs. State-of-the-art neural networks can contain billions, even hundreds of billions of neurons, which explains how they have become so powerful over recent years. Okay, two more slides today, and this is another one that's a little bit more of a reference as you may come across this terminology in the future. But the motivation for this slide is to give you a little bit more perspective into how during model development we use a collection of data called training data to teach those artificial neurons that we talked about in the last slide to learn how to recognize patterns and generate desired outputs. With that in mind, we'll talk about three general techniques for training machine learning models, which are ultimately determined by the nature of the data that you have available to you during model development,
as well as the specific task that you're hoping to perform.
First, we have supervised learning, and this is when you have data that comes in the form of input and desired output pairs. For example, you may have 1,000 x-rays, and for each x-ray you have a label of whether or not it contains pneumonia. You can then show the model, here's the image, it has pneumonia. Here's an image, it doesn't have pneumonia, etc., etc. And as you proceed through that training process, the model will learn to recognize the patterns needed to determine whether or not pneumonia is present. Learning is great when you have a clearly predefined task and it's feasible to develop enough labels to train a model to perform that task. However, this is not always the case. Self-supervised learning is a technique that can be used to take a large corpus of unlabeled data and effectively transform it into a supervised learning problem. Classically, this is performed by showing the model part of a piece of input data and asking it to predict the rest of that input data. For example, language models, which we will discuss in great depth later in this course, are typically first trained by showing the model a chunk of text and forcing it to try to predict the continuation of that text. Self-supervised learning techniques have been shown to be extremely powerful because it enables us to expose the model to extremely large quantities of data in a fashion that forces the model to learn key patterns, which back in our language model example may be things like basic grammar, vocabulary, and style. Finally, in reinforcement learning, we set up a model to be able to perform specific actions, and then we provide it feedback, positive or negative, to guide the model towards desired behavior. With language models, for example, reinforcement learning techniques may be used when you have a model that's capable of producing coherent text and you want to guide it towards a specific style of response. Okay, so by now we're familiar with all the basic components of a modern AI system, including the types of inputs it may take in, the types of outputs it may generate, and a basic understanding of the types of models that sit under the hood and the techniques that we use to train them. Some of the information in this lecture has been a bit technical and may seem disconnected from clinical medicine, especially relative to future lectures in this series. So I therefore wanted to close with a few thoughts on why it's so important that clinicians and future users of these systems have a basic understanding of how they work and how they're developed. The reason for this is because no artificial intelligence system operates in a vacuum, and it is impossible to separate the function of these systems and their efficacy from the entire healthcare workflow that exists before and after them. For example, as we'll explore in greater depth and with concrete examples throughout this series, many AI systems are extremely sensitive to small changes in their inputs, changes which only you, as their users and experts in the clinical context, may be able to anticipate and detect as they play out in real time. Similarly, an understanding of a bit of how the models work, their pitfalls, and how they're distributed can help you to become a more effective user of these systems and advocate for your patients. Finally, as you become a user of AI systems, potentially in high-stakes clinical settings, it will be important to understand the bidirectional interaction between the output of these systems, the healthcare systems that use them, and even your own cognitive processes. In our next modules, we'll finally turn towards clinical medicine specifically, exploring the promises and the pitfalls of clinical artificial intelligence.